One of the important theorem in the study of topology is called Tychonoff product theorem, which says that arbitrary product of compact topological spaces is compact. We shall prove this theorem later in general. In the present module, we shall first prove that finite product of compact spaces is compact. Then we shall introduce another way to explain compactness, which call filter. We shall introduce the notion of ultrafilter and prove that a space X is compact if and only if every ultrafilter on that space converges. Let us pass to the slide presentation. In this module, first we prove that finite product of compact space is compact. To prove this theorem, first we require the following lemma. The lemma said this: if X and Y be two Hausdorff space with Y compact, then for any X belongs to X and any open set N containing the slice singleton set X Cartesian product Y, there exists a neighborhood W of X in capital X such that W Cartesian product Y is contained in N. For example, the tube lemma is certainly not true if Y is not compact. Let us consider Y be the Y axis in R2. Since Y axis is homeomorphic with R and R is not compact, so Y is not compact. Now consider the set N is equal to all xy such that modulus of x less than 1 by 1 plus y square. Then clearly N is an open set containing the set y axis, but it contains no tube containing the set y axis. So, let us come to the proof of tube lemma. Let X belongs to capital X and N be an open set in X Cartesian product Y containing the slice X cross Y. Now, the mapping P2 restricted on the slice X cross Y from X cross Y to Y is a homeomorphism. Since Y is compact, therefore, the slice X cross Y is also compact. And we can find a minimal finite subfamily of script B, each contained in N, whose union contains the slice X Cartesian product Y. Let us label the members of this finite subfamily as U1x Cartesian product V1x, U2x Cartesian product V2x up to UNX x Cartesian product VNXS. Now, let us set W is equal to intersection UIX, I runs over from 1 to Nx. Then the slice x cross y is contained in W cross y subset of n, where W being finite intersection of open set is also open. Now, we are in a position to prove that x cross y is compact if and only if both x and y are compact. One part is very much clear, that if x and y are compact, then each factor space is compact, because projection maps are continuous and compactness is preserved under continuous image. Now, to prove the converse, let us first recall that a space is compact if and only if every open cover by basic elements has a finite subcover. We have already mentioned this fact, that to prove the compactness, it is sufficient to consider basic open cover. Now, suppose both x and y are compact spaces, and let B be an open cover of x cross y by basic open sets of the form U cross V, where U is open in x and V is open in y. We have to prove that B have a finite subcover. Since y is compact, we have that the slice x Cartesian product y is compact. Now, the collections cube B which covers x cross y should cover the slice x cross y. So, we can find finitely many elements of cube B, say B1, B2, Bk, whose union contains the slice x cross y. Now, let us take n is equal to union of B1, B2 up to Bk. Then n is an open set containing the slice x cross y. So, by tube lemma, there exists an open set W x of x in capital X such that W x Cartesian product y is contained in N. Now, consider the collection W x such that x belongs to capital X. This collection forms an open cover of x. Since x is given compact, we can choose x1, x2, xr in capital X such that the open sets Wx1, Wx2 up to Wxr covers x. Then let us consider the sets Wx1 Cartesian product y, Wx2 Cartesian product y up to Wxr Cartesian product y. Observe that each Wxi Cartesian product y is contained in N, and their union cover x Cartesian product y. That means x Cartesian product y is contained in the union of Wxi Cartesian product y, where I runs from 1 to r. Since each can be covered by finitely many elements of script B. So, X Cartesian product Y can also be covered by finitely many elements of script B. Hence, X Cartesian product Y is compact. This completes the proof. Next, we state another very important theorem which is called extreme value theorem. We have already proved that continuous image of compact space is compact. This helps us to generalize the result from elementary calculus. If X is a compact space and f from x to R is continuous, then f is bounded and attains its maximum and minimum values on x. What happens in the proof? In fact, since x is compact and continuous image of compact spaces is compact, so we have f of x is compact. So, f of x being compact subset of R is bounded and closed, hence its supremum and infimum exists and belongs to f of capital X. Therefore, there exist elements in capital X whose images are supremum and infimum of f x. That means, f attains its bounds on x. This proves the extreme value theorem. Next, we state another important theorem which is known as Lebesgue number lemma for the case of compact metric space. This theorem is of extreme importance. In fact, in the study of algebraic topology also this theorem is required very much. Let us state the Lebesgue number lemma. Let X be a compact metric space and script U be an open cover of capital X. Then there exists a positive number delta such that any subset of capital X with diameter less than delta is contained in some member of script U. That means, Lebesgue number lemma says that given an open cover of a compact metric space, there exists some number delta such that every subset of X with diameter less than the delta is contained in some member of that open cover. This number delta generally called Lebesgue number. Before proving this theorem, let us state an example. Let f from closed unit interval 0 1 to S1 be a continuous map, and let U is equal to S1 minus I and V is equal to S1 minus I. Then there exists a partition of 0 1 such that f of xi to xi plus 1 is contained either in U or in V. This example is required to calculate the fundamental group of S1, which is the part of algebraic topology. We shall not describe it here, but to prove this example, as U and V are open sets in S1, then F inverse U and F inverse V are open sets in closed unit interval 0 1, and they cover closed unit interval 0 1. So, there must exist a Lebesgue number. Say the Lebesgue number be delta. Therefore, by Lebesgue number lemma, we can say that any subset with diameter less than delta is contained either in F inverse U or F inverse V. Now, we take a partition of the closed interval 0 1 such that the norm is less than delta. Then every subinterval has norm less than delta. That means, if diameter of every subinterval is less than delta. So, every subinterval is contained either in F inverse U or F inverse V. That means, image of every subinterval under F is contained either in U or in V. Now, we prove the Lebesgue number lemma. To prove this, let script U be an open cover of a compact metric space X. Now, for each X belongs to capital X, there is some open set U in script U. Since U is open, there exists some positive number, let us say it as Rx, such that the open ball centered at x of radius 2x is contained in U. Now, consider the balls B Rx such that x belongs to x. That means, consider the collection of all open balls centered at any point of x with radius Rx, where Rx is the corresponding real number to x. Then this is an open cover of x, and as x is compact, it has finitely many subcover, say Brx1, Brx2 up to Brxn. Now, let us take delta as minimum of the real numbers Rx1, Rx2, Rxn. We claim that delta is the Lebesgue number for the open cover script U. That means, any subset of x with diameter less than delta is contained in some member of script U. To see this, suppose S subset of capital X is a non-empty set with diameter less than delta. Let y be any point of S, then there is some point xi such that y belongs to Brxi xi, as Brx1, Brx2 up to Brxn cover x. Now, it suffices to show that any other point of S is in B2R xi, since the latter set is by construction is contained in some u in script u. If Z belongs to S, then the triangle inequality gives dzxi less or equal to dzy plus dyxi less than delta plus rxi less or equal to 2rxi, which proves the claim. Next, we present an alternative criteria for compactness. In fact, except first countable spaces, sequences are not sufficient to describe topology. To overcome this, we generally need the concept of filter or net. Here, we shall introduce the notion of filter, and using this we shall introduce the notion of ultrafilter, which will help us to give another alternative characterization of compactness. Let us come to the slide presentation. Let us come to the definition of filter. A non-empty collection script f of a set X is said to be filter if number 1, script f does not contain the empty set. Number 2, script f is closed under the intersection of finite intersection. That means if f1 f2 belongs to script f, then f1 intersection f2 belongs to script f. Number 3, script f is closed under the formation of superset. That means if f belongs to script f and G contains f, then G also belongs to script f. Some authors avoids the definition 2 in this way, that if f1 f2 belongs to script f, then there exists some element C in script f such that C is contained in f1 intersection f2. Now, a filter is said to be an ultrafilter if it is not contained in any other filter properly. So, it is very natural to ask whether there exists an ultrafilter. By Jones' lemma, it can be easily proved that every filter can be extended to a ultrafilter. Let us define two types of filter, fixed and free. A filter is said to be fixed if the intersection of all its elements has a non-empty intersection, and free if their intersection is empty. For ultrafilter, the case is also same. That means an ultrafilter script u will be called fixed if there exists some x belongs to capital X such that x belongs to intersection of u such that u belongs to script u, and if intersection of script u is empty, then the ultrafilter will be called free. It can be easily shown that a characteristic property of a filter being ultrafilter is that for any subset A of X, either A belongs to that F or complement of A belongs to F. It is easy to find example of fixed ultrafilter. For example, let X be an infinite set, small x be a point of capital X, consider all subsets of capital X which contain small x. Then this becomes a fixed ultrafilter containing X in capital X. Now, an example of free ultrafilter is the collection of all cofinite subset of X. Now, let us introduce the notion of convergency for ultrafilters. Let capital X be a topological space. Note that to define filter or ultrafilter, it is not necessary to consider a topological space, but here we are considering the convergency for some topological space. Let X belongs to X and script U be an ultrafilter on the topological space X. We say that script U converges to X if every neighborhood of X belongs to script U. We have observed that in a Hausdorff space, a sequence can have at most one limit. That also true for ultrafilter. That means in a Hausdorff space X, every ultrafilter can have at most one limit. In fact, this is the if and only property. If X is Hausdorff, then every ultrafilter has at most one limit. On the other hand, if in a topological space every ultrafilter has at most one limit, then the topological space is Hausdorff. First, let X be Hausdorff and script U be an ultrafilter on X. If possible, X and Y be two limits of script U. Then the neighborhoods of both X and Y are contained in script U. Since X is Hausdorff, X and Y must have disjoint neighborhoods. That means script U is an ultrafilter which contains two sets which are disjoint. That is a contradiction. So, in a Hausdorff space, an ultrafilter can have at most one limit. Conversely, let any ultrafilter has at most one limit. We have to show that the space is Hausdorff. So, let us consider two distinct points X and Y. Then we can consider two fixed ultrafilters Ux and Uy. Then there exists A belongs to Ux and B belongs to Uy, which are disjoint. Since X, Y are limits of Ux and Uy respectively, we must have that X is Hausdorff. Now, we are presenting our final characterization of compactness using ultrafilter. A space X is compact if and only if every ultrafilter on X is convergent. Every filter has finite intersection property, and that every collection of sets with finite intersection property is contained in an ultrafilter, which can be proved by Jones lemma. Therefore, using the finite intersection property of compactness, that is, a space is compact if and only if any collection of closed sets with FIP has non-empty intersection, we can prove the theorem. So, in this module we have seen that finite product of compact space is compact. We have also learned an extremely important theorem called Lebesgue number lemma, and finally we have given an alternative characterization of compactness using ultrafilters. With this we end this module. Let us pass to next module.